Hey, calculus learners, this is video 1.2.6 where I'm trying to connect the function notation practice you just did and transition you into the world of calculus. So let's start that out with a little game. So hopefully you can see this whiteboard screen. And I'm going to give you a few function points and see if you can find the pattern. So let's say I started this way. Started with, okay, I told you all that f of 3 equals 9. I'll give you some more information. I'll give you that f of 5 is equal to 15. Right now you're trying to figure out, okay, can I predict this next relationship? So f of -2, maybe you're already ahead of me, is equal to -6. And I think with that information, you could probably guess, I asked you, okay, based on this, this function that you're seeing, what do you all think f of 7 is? So just pause for a second and see if you can figure it out. Well, hopefully you got that it would be 21. And if I were to ask you, okay, so what's this function? Well, this is f of x, just f of the input value is equal to 3x. Whatever input you give, you're multiplying by 3 to get the output value. And that's just a function, that's a line, stuff you've seen before. So I bring this up to sort of transition you to the world of calculus. So if we actually looked at a graph real quick, I'm going to share my screen here and looked at this Desmos graph. So we're seeing right here the function we just saw. And all those pairs we would see really clearly as input-output pairs. And reminder, you saw it in the Professor Wu video, you saw it in these previous videos with Sal Khan, that a function is just I put in a certain input and I can get a predictable output. And so I could really easily see these ordered pairs if I put 3, 9, I labeled it, you can see like that input output is directly on that function. I could even just put, because Desmos is cool, I could put f of 5 and it'd tell you, yep, 15 is on the function. I could put the whole point -2, -. You can see that these on the function. I bring this up because function notation is really similar, but importantly different from calculus notation. So if I were to word, let's look at how we did for f of 3. So when I did f of 3, we got 9. So what calculus is going to do is not use the same function notation language. So I'm going to annotate real quick. So right now, when you're saying f of 3, the corresponding math language is this. It's saying when x equals 3, what is the y value or the output value? Well, if I was analyzing this function with calculus language, I would ask a slightly different but really important question. And I'll show you the language to start off with. So right here, what you'll see with calculus language is this. You'll see stuff like the limit. Again, LIM is just short for limit. The limit as x approaches 3 of this same function f of x, we would also say is 9. The important difference is calculus language is asking a different question. So function notation is saying, when this is the input, what's the output? Can you tell me the y value? Calculus language is saying this. It's saying as x, I'll say as we get closer and closer to where x equals 3, what is the y value or the f of x, which is the output value, getting closer and closer to? So it sounds really similar, but it's sort of like, imagine, like, look at my mouse real quick. Actually, I can use the annotate to make it even more clear. Let's say I was, approaching, I was on this line, like I'm traveling on it. As I get closer and closer and closer to x is 3, it's like down here I'm at x is 1, and then I get to x is 2, and I'm right about x is 3. And if I actually travel to it from the other direction, it's asking, okay, as I get I kind of pinch this point, as I get closer to it, what is the y value? And so when it's a function like this, when you're dealing with function notation and limit notation, it's the same thing. Like when x is 3, y is 9. When x is 3, the output is 9. So no matter if I pinch it from both sides, if I just look at it, it's the same thing. The reason this is really important is because right now we're just analyzing a linear function. We're going to analyze a lot more complicated functions. So stuff like, clear my annotations real quick, stuff like this, these rational functions. And so, we can still use our function notation. So for example, we can see really clearly the point 1, 0 is on this function. So if we asked like, what is f of, and I guess we're dealing with g, what is g of 1? Well, it's 0. When I plug in one function, I get 0 the output. The same would be true for the limit. If I wrote, I'm going to show you all some more annotations just to get that calculus language flowing. If I wrote this, if I was wondering, okay, as x gets closer to 1 on the function g of x, just like with function notation, I would say the limit is 0. So as I get, kind of approach it from both sides, getting closer to where x is 1, it looks like the y value converges to be 0. As I get closer and closer to it, what's the y value? The reason limit notation is really powerful is if I asked you all the question, what is f of 2? Well, you might notice we could factor this bottom to be x plus 2 and x minus 2. And so if I ask you what's f of 2, before calculus, we don't really have an answer to that. We're like, it's not defined, it's not on the function. But what's really powerful about calculus language is calculus can actually answer that question. Calculus can say, okay, I don't know the exact output, but I can wonder, I can be curious and say, I wonder as we get closer and closer to 2, as we approach it as close as we can onto infinity, what's this limit? I'm using g of x, that was silly of me. And this should be g of x over here, be better than me. As I get closer and closer to where x is 2, what's the output? In this case, I would actually conclude that it does not exist. This limit doesn't exist here. We'll talk about why. If it were a one-sided limit, it would exist. So I know I said calculus has the power to analyze this. It does, not the way we wrote it, but calculus gets to grapple with this kind of stuff. So when the function notation fails us, calculus language still gives us a tool to make a prediction about what is the limit, what is the y value, even on functions we can't analyze the end result for. So I hope that was helpful for an intro to this. I have 2 more coming up that might make it even more clear. As always, if you have questions, let me know.